Mistral, it's a French AI startup. Recently unveiled its first large language model, Mistral 7B, which is free to use without any restrictions. It can be downloaded via various means, including torrent, and it's also shared on GitHub for collaborative development. So now we are going to look at the source code of Mistral SRC. So this particular code snippet, it's basically a list of import statements, and it imports necessary libraries and modules for working with the language model. So the first thing is the first import statement. It's basically importing a cache for managing the data, which is a rotating buffer cache. Then it imports the PyTorch, which is the library for managing multidimensional tensors, and then Fire, which is library for handling command line interfaces, and then the type hinting package, and then it imports the path from pathlib package, mainly to deal with file system access or file system paths, and then it imports a transformer model and a tokenizer from the Mistral package. So these two are likely to be used in processing the textual data. Let's look at this function, sample Topies function. So this function implements Topies sampling, which is a method used in large language models for text generation. So it receives a tensor of probabilities, probs, and the threshold p, and then it returns a sampled token index. This line is an assertion check. So this line is an assertion check to ensure that the value of p is between 0 and 1 inclusive. So if p is outside the range, then there is an exception thrown or an error assertion error thrown, indicating that this program has a bug, right? So now the next line, which is where the sorting is happening. So it sorts the tensor probabilities in descending order along the last dimension. That's why we have dim equal to -1, and it returns two tensors, prop sort, which contains the sorted values, and then props index containing the indices of the sorted values in the original props tensor. So, so the original prop tensor contains the unsorted values. So props index contains the indices of the sorted values in the original props tensor. So next we have the cumulative sum line. So this is where it computes the cumulative sum of the values in the sorted probabilities tensor along this last dimension. So this results in a tensor which is prop sum, where each element is basically the sum of all the preceding elements along this dimension, the last dimension. Then we have the mask, Boolean mask creation. So what this does is it computes the difference between prop sum and the sorted probabilities tensor. So it checks if the result is greater than p. So what happens is each element in the mask, it will be true if the corresponding element in this difference is greater than p. Otherwise, it will be false. So that is the Boolean mask here. So here what we do is it is zeroing out the probabilities based on the mask. So that particular index, it is zeroed out. So what happens is when the probabilities are zeroed out, it keeps the cumulative probability below p. So that's the basic idea. Now we have the next line. This is where normalization is happening. So the sorted probabilities tensor, it is getting normalized by dividing each element by the sum of all the elements along the last dimension. So this method div underscore method, it performs this operation in place. So it means that it is modifying the sorted probabilities tensor without creating a new tensor. That is the in place operation. And this parameter keep dim true. It ensures that the sum operation retains the original number of dimensions. So this particular parameters value equal to true is necessary for the division to be broadcasted correctly. So this line, if you see, it is using the PyTorch multinomial function to sample a value from the distribution. So it is sampling one value from this distribution. The sampled value is it's an index that is assigned to the next token. So the next line, which is the return statement, it uses the torch gather function to collect the values from the indices tensor based on the index which is arrived in the previous line, which is present in the next token. So the result is a new tensor containing the values from the indices at the position specified by the next token. So this is the summary of this function, sample top P function. Now let's look at the sample function. So this function, it samples the token based on the input logits with the optional temperature scaling and top P sampling. So what it does is it checks the temperature value. If the value of temperature is it's greater than 0 or not, and then so yeah, so if the value of the temperature is greater than 0, then it scales the input logics tensor. It computes the softmax using the from the PyTorch library, and then it invokes sample topi to sample a token. Otherwise, if the temperature is not greater than 0, what it does is it basically finds the argmax of the largest tensor, and that is taken as the next token. So the final line is the return statement. It returns the next token, which is reshaped into a one-dimensional tensor. So now let's go line by line. So what happens in this line is that a division is happening. So each element of the logits tensor is basically divided by the temperature, and then the softmax function is applied along the last dimension. So this basically produces a probability distribution, hence the variable name props, and this distribution is across different classes of the tokens. So what we need to know is that about the softmax function is that it is very important here. So it is converting this logits tensor into a probability distribution. So that probability distribution is very much needed for sampling the token, and that will be required in the subsequent steps in the function. So this kind of probability distribution or the probabilistic interpretation, it allows for some kind of variability or some kind of uncertainty to choose the next token. So that is very important in the tasks for large language models, for example, text generation task. So now let's look at the next line. So here we have the invocation of sample topi function. So wherein the probability distribution is passed, and even the topi value, which is the input, it is also passed as the argument. So Basically, sample topi function, it samples the token according to the Topies sampling strategy. So now that is assigned to the next token. The sample token is assigned to this particular variable next to. So in the else block, if we see, what happens is that we are using the argmax function. So it finds the index of the maximum value in the logic's tensor along the last dimension. So which could probably considered to be most probable token. And this unsqueeze function, it adds an extra dimension to the beginning of the tensor. So basically, from an one-dimensional tensor to a two-dimensional tensor conversion is happening with one row, and that is assigned to the next token. And then the final line, which is the return statement, it is reshaping the next token into a one-dimensional tensor by doing some flattening. So it is ensuring that it has a single dimension regardless of its original shape. And this reshaped tensor is what is returned by this function, sample function. Yeah. So let's now look at the generate function. So this function, it takes multiple parameters. So one is the list of prompts. So basically it's a list of string, and then it takes the transformer model as one of the inputs, and then the tokenizer, and then the max tokens, which is an integer, and then what is the chunk size, and then the temperature. So it just to summarize, so it basically expects a list of string prompts. There is a transformer model, a tokenizer, an integer which is max tokens, and then the star, which is basically optional parameters, and then the chunk size and temperature. So temperature, basically the default value is 0.7, and then chunk size, the default value is none. Now if we go to the first line, so first line, what we are doing is, that is line number 35, what we are doing is we are setting the model to evaluation mode. So setting the model to evaluation mode, it affects the layers like dropout layers. So we'll come back to this. So this line, what it does is it assigns the number of prompts to B, and then it sets the vocabulary size to B. So that vocabulary size comes from the model itself. So we have this model object. So from there, the vocabulary size is set to B. So then now, if we go to line number 39, so here the tokenization is happening. So what it does is it tokenizes each prompt. So as you can see, this is a list of prompts. So it is tokenizing each prompt, and so the BES basically means that beginning of sequence. So it adds a beginning of sequence token as well. Then here what happens is, so we have an internal for loop logic. So it computes the sequence length of each encoded prompt. So here we have this encoded prompt, and so what it does is it computes the sequence length of each encoded prompt, and that is set to sequence length variable. So just to come back to this line 35, setting the model to evaluation mode. So as I said earlier, it ensures that certain layers like dropout. So there are also other layers like batch normalization layers. So they behave differently during evaluation than in the training mode. So in evaluation mode, the dropout layers, it doesn't drop the activations, and batch normalization layers, it will use running estimates instead of batch statistics, so that this provides consistent output for a given input. So if, let's say, if we do not set the model to evaluation mode, then what can happen is it can lead to inconsistent and incorrect outputs during the inference mode, because the dropout layers and batch normalization layers are active. So it will behave as if the model is still in training mode. So this actually, in fact, it affects the performance of the model and even the predictions, whether it's reliable or not. So that also it affects. So now going to line number 43 onwards. So here what is happening is it sets the cache window to the minimum of the sliding window, or it takes into consideration the sequence lengths. Here we took the encoded prompts, the length, so the max of sequence lengths plus max of token. So max of token is one of the arguments. So in line number 44, rotating buffer cache, so what was imported earlier, so that is initialized with the parameters from the model. So there are so many parameters within the model, for example, number of layers, what's the max batch size, and then the cache window, which was just initialized in the previous line, and then number of kb hertz and the head dimension. So all these are basically inputs to initializing the rotating buffer cache. So now line number 45. So what happens is here the cache is moved to the model's device, and the data type is also set. So in line number 46, the cache is reset. So it clears any stored data. So since in the previous step it is moved to the device, so here it is cleared. So line number 49. So here again it's some again it's an initialization. So it initializes log of probabilities as a list of empty lists, that is for each prompt. So we saw in line number 36b is initialized to the number of prompts. So those many empty lists have been created. Now in line number 58, so it sets last token pre-logits to none, and in line number 53, so the max prompt length is set to max the length of the longest prompt. So max of sequence length we saw here, so it sets that to the length of the longest prompt. And here in line number 54 and 55, so if the chunk size is not actually specified, then the chunk size is set to max prompt length. So that's it for these many lines. Yeah, so continuing on the generate function, so here we have a for loop. So now we have focusing line number 58. So it is iterating from 0 to the max prompt length in steps of chunk size. So what it does is in line number 59, it is slicing the encoded prompts into chunks, and where each size of the chunk is the chunk size. And then it does an assertion. So the assertion is that each chunk it actually has length greater than 0. So it should be non-zero. And then what happens in the next step is model dot forward is invoked, wherein the prompt chunks are actually concatenated, and then it also passes the cache and the sequence lengths, and the result of the forward pass is stored in pre-logits. So then the next step is the log probabilities from the pre-logits are computed using the softmax, and then it is stored in logits. So one thing to note is that in the world of transformers, model forward is the method which passes the input data through the model to produce the output. So this model dot forward, it encompasses the entire forward pass of the model, executing operations in the model's architecture. So the operations could be something like self-attention and feed-forward networks, and finally it returns the logits or other outputs. It could be depending on the input data. So in this code, if you see this line, the softmax, it computes the logarithm of softmax values of pre-logits along the last dimension. So what softmax it does is that it normalizes the pre-logits into a probability distribution, and logarithm on top of that, it makes these values more numerically stable. So in the sense that during propagation, it is more stable in the training phase. So in this code block, the last token logits, it is utilized to obtain the log probabilities of the first token in each current chunk of the sequences. So these log probabilities are then appended to the corresponding list in log probs to accumulate the log probabilities of tokens for each sequence over the processing of chunks. So here basically some kind of appending is happening, and and then it checks that yeah, so this line, it actually checks if the last token pre-logits is not none. So that means it is not the first pass. It is basically from the second pass onwards. So here it again computes the log softmax of this particular variable last token pre-logits along the last dimension. It assigns that to last token logits, and then this particular for loop, there is an iteration over the sequence. It appends the log probability of the first token in the current chunk to log props within that particular index. Now this particular chunk of code, so here the offset is initialized to 0, and then here again we have a for loop. So there is an iteration which is happening over the prompt chunks, wherein the log probabilities, it is extended with log probabilities from logits. So here you have log probabilities, it extended with log probabilities from the logits. So for each token it is done except the last one. So then the offset is updated by adding the length of the sequence so that you have correct indexing in the next sequence. So this line 79, so here what is happening is um, it is computing the index for the last token of each chunk, and it selects these entries from pre-logits to update the last token pre-logits. And finally, there is an assertion wherein it checks the last token pre-logits has the expected shape. Yeah. Yeah. So moving on, so this is a part 3 of generate function. So this is the decode step, the encoder decoder architecture of transform. So here is the decoding step. So on line number 83, the empty list generated tokens, it is initialized, and then here we have an iteration of the max number of tokens. So in this step, the sampling is happening to retrieve the next token, and here the last token logits is computed, and the log probabilities is appended to log props. And then here on line number 91, basically the generated tokens is appended with the next token, so which is retrieved in line number 85, and in line number 92 last token pre-logits is computed. That is computed for the next iteration by passing the next token through the model. So here the forward pass is happening on the model. So since we have already sampled the next token, so the last token pre-logits is computed. And then finally, we are ensuring that the last token pre-logits, it has this expected shape of B and V. So here, just a recollection of the sample function. So sample function, it contributes to the token generation by selecting the next token based on the provided pre-logits and the sampling parameters, which is temperature and the Topies parameter. So sampling, it basically encapsulates the logic for either sampling from the probability distribution or taking the most likely token. So it aids in creating a sequence of generated tokens in a controlled manner. So that's what is happening in the decode step. So now next we shall be moving to the generated words. So from the tokens we need to realize the words. So let's move on. So this is the final step in this generate function. So here what happens is it initializes an empty list generated words, and then whatever generated tokens was available in the previous step, it is checking if it is not empty. If it is not empty, then it is concatenating generated tokens along the first dimension, and then there is a iteration happening over the encoded prompts. So what is happening is it is again concatenating um, each with the corresponded generated tokens, and here it is decoding the generated tokens into the words, and it is appending to the generated words list. So here we can see the tokenizer, the internal tokenizer of the model. It is decoding the word, and it is getting appended into the generated words. And finally, the generate function, it returns the generated words and also the logarithmic probabilities. So here you can see that combining encoded prompts and generated tokens. So here you can see X plus generated tokens. So combining both of them, it basically reconstructs the complete sequence. So it integrates the original prompt with the newly generated token. So this way, each entry in the generated word, it reflects the combination of the original prompt as well as the generated content. So that's the idea here. So the output, it basically retains the context provided by the prompts. So now if you need to go a little bit deeper into decode, so what is happening is the token ID, it is converted back into words by mapping each token ID to its corresponding word or subword in the tokenizer's vocabulary. So in the beginning of our generate function, we might have seen the model's vocabulary, right? So which is where there is something like a mapping between the token and the word. So these are all concatenated together, and it also typically is concatenated with spaces so that human readable text is formed and it is generated and given back to the user. So that's all happens in the last step. Yeah. Moving on, next we have an interactive function. So this interactive function can be used, can be invoked by the user if the user wants to provide some set of prompts to test the model or to see how the model behaves. So here we can see that there are few parameters for this interactive function, and so in line number 105 and 106 you can see that tokenizer and transformer, it is getting initialized using the model path. So then onwards it enters a infinite loop. So within infinite loop, we can see that it is taking the input from the user. It is stored in the prompt variable, and then we can see that the generate function is actually invoked with the user input prompt and the other parameters, which is the transformer and tokenizer from the model, and then it prints the whatever generated word or generated response, you would say, from the generate function. So generate function, it utilizes the tokenizer to basically convert the input prompt into the token IDs, and the transform is used to process these tokens to produce new tokens. So tokenizer, it encodes the prompt into a format the transformer can understand, and later it decodes the generated token IDs back to the words or the text. So transformer, it processes the tokenized input to generate token IDs for the next tokens based on the input and the model's learned patterns. So that's what is the responsibility of tokenizer and transformer within the model. And if you remember, there was a cache in the generate function. So that cache, it stores the intermediate representation, so that in the subsequent forward passes we can reduce a lot of computation, so that the generation process is made more efficient, so that when we are generating sequences token by token, it is a lot faster if we have a cache. So that's all about this interactive function. Yeah, so this is the last function in the main.py for the Mistral model source code. So this is the reference implementation source code, and now we are looking at the demo function. So the demo function is similar, almost similar to the interactive function, just that in the interactive function the user provided their own set of prompts, whereas in the demo you just have some set of demo prompts. So what happens is, yeah, again it is initializing tokenizer and transformer from the model, and then it is calling generate function with the predefined prompts. So it iterates through the results. So for example, here you don't have the infinite loop which we saw earlier in the interactive functions. So here it iterates over the result. It prints the generated text along with the separator line. So the last chunk of code is nothing but the entry point for this main.py. So it is basically using the Fire package to allow the command line interaction for interactive as well as the demo function. So that's all for the demo function. Yeah, thank you for watching. I hope this video helped you to understand the source code for the reference implementation of Mistral language model. I hope it helped you in the world of large language models. So please subscribe to my channel to support me. Thank you, and if you have any comments, please let me know. Thank you.